Breadth first search is a little different. The idea with breadth first search is you basically try visiting one step in each direction repeatedly until you find a solution. So some students have a little more trouble understanding this algorithm, but just conceptually, like if I'm trying to get from A to, I guess I'm going to I this time, basically I go one step out in each direction, then I go one more step from there, then I go one more step from there, then I go one more step from there, and eventually I find a path. Now, I probably made it sound like this is some kind of parallel algorithm doing a bunch of things at the same time. That's not really what it's doing. It basically says for each unvisited neighbor, explore them, and then for each of their unvisited neighbors, explore one of them. And it is doing them in a certain order. So I'm adding B and D and E. So now I'm adding G and H and F. I can get to these vertexes that are one more square away, kind of in order of who the neighbor was that got me to them. And eventually I get to H and I get to I. So this one, the coolest thing about this algorithm, as opposed to depth first search, is it will always find the shortest possible path. I don't know if you can just trust me on that, or if you have an intuition for why that is. Like, can you does somebody have a good way of describing, like, why am I pretty sure that this will find the shortest path? Yes?
So it's basically each round is adding one step, and so if it hits what you're trying to find during that step on any of the different searches that you're going through, then it will return that given path, and it won't go on to the next round, taking another step,
right,
until all of them have been checked.
Yeah, you're right. Like each round, I'm adding kind of one more step to the chain, like you said. And the way I think of it is, at this point in the algorithm, I've tried all the possible paths of length 2. And at this point, I've tried all the possible paths of length 3. And at this point, I'm trying all the possible paths of length 4. And if I find an answer here, and you say, oh, 4, okay, but let's do proof by counterexample, right? Or by contradiction, I guess I mean. If we find a path of length 4, you could ask, is this the best one? Would there have been one of length 3 or one of length 2? Well, if there had been, we would have found it up here, and we would have stopped up here, and we didn't. So we must not have been able to find it. Do you understand what I'm saying? Like, by contradiction, we wouldn't have got here if there was a shorter one up above. We already tried everything shorter before we got to this point. Anyway, that's the intuition of why this thing is going to find the shortest possible path. In terms of how it actually works, here's kind of a pseudocode description. I mean, I kind of described it already, but here's the way the thing works. I'm going to do this as a Socrative. So let me clear out the Socrative again. Can't I just say new question? Yeah. OK, there we go. So here's another Socrative question. Here's the pseudocode for this one. What you usually do here is you don't actually do it recursively. Usually you just keep a queue of what vertexes you are going to look at next. And here's what you do. Initially, the queue contains only the starting vertex, which you mark as being visited. And now, while the queue isn't empty, you remove something from the front of the queue. And if that's your destination, you can stop. But otherwise, you look at that thing that you just removed from the queue and look at all of its neighbors and which of its neighbors are not visited. Whatever neighbors are not visited, you add those to the back of the queue. And the algorithm just keeps going. And the result of that algorithm is the crawl that I showed you a second ago on the previous slide. So in light of that, what path would it find from A to F? I guess it's hard to read. It's on the bottom of the slide. Choice A says it would find the path AEF. Choice B says it would find the path ADHF. Choice C says it would find ADGHF. And choice D says it would find the path ABF. So which one does it find? I'm going to give you a lot of time to think about this one. So I'm joking. I'm not going to give you very much time at all. You guys get it, right? Like A is the right answer, which is the path AEF. Why is AEF the right answer? Well, I mean, I guess the thing is, it's kind of easy to do these as Socrative answers because you just look at the graph and you can just figure out what's the shortest path. AEF, that's the shortest one. All these other ones aren't as short, right? So these other answers aren't going to be right, except for like D is just as short, but that isn't even a path. You can't even go from A to B to F. So anyway, A is the right answer. That's what BFS would find. Now you might say, this seems better than that depth first search, right? I should just use this one. This one's better. But this is not universally better. this algorithm is a little bit harder to code than DFS, and also the runtimes can be a little different, and the amount of storage and the amount of space and memory and stuff that they take when they run can be different. So this is not universally a better algorithm. It just has certain properties that we might want, like finding the shortest possible path. In terms of analyzing the algorithm, I mentioned it has this optimality property. It finds the shortest path with fewest edges. One thing about it is that it is a little bit trickier to reconstruct the path. With DFS, you just passed along a vector or something, and you add things to it, and unchoose, you remove things from it. You can't really do that here, because conceptually, you're sort of partially exploring lots of paths at the same time. And so you can't keep vectors for all of them, although you can, technically. In fact, you did. I don't know if you realize it or not, but you've written this algorithm. Do you know what I'm referring to? When did you write this algorithm?
Word ladder?
This is what word ladder does. Yeah. I mean, maybe it's not clear just looking at these slides, but like word ladder is you try all the ladders that are one letter away from the starting word. Then you enqueue a bunch of stacks of all the word ladders that are two letters away from the starting word, right? That's a breadth-first search. If you think of words as vertexes and edges between words that differ by one letter, what you wrote for assignment 2 is this in that context, basically. So one way you could retrieve the path that you took would be to keep a whole bunch of partial paths in progress as data structures. That's what you did for assignment 2. You had this giant collection of stacks, and when you finally found the right path, that little stack was the path, and you just popped all the elements to print out the path that you took, right? But in general, that's not a practical thing to do, because you have to store a ton of data to accomplish that. And that's just not very efficient in the computer's memory. So that's not usually what we do. What we usually do instead, and I think my next slide will show you this, is that we sort of keep track of each vertex's previous vertex, and that will give us breadcrumbs that we can use to find our way back to the answer. I'll show you in a sec. Hey, Kevin, did Kevin just come in? Hi, Kevin. Hey, buddy. Hey, are you hours today?
Yeah, at 6:30 in Hewlett 201.
6:30 p.m., Hewlett Building, room 201. Remind me again at the end of class, because I'll forget. I'll say it again when we're done. Thanks, Kevin. I appreciate that. OK. So let me see if I can show you the version of this that has those previous pointers. Here, there we go. Now, this version of the algorithm is basically the same. The one thing that I added was when you are enqueuing new vertexes into the algorithm, you say, hey, I got to that new vertex from V. V's neighbor is N. That's how I found N. So I'm going to tell N that his previous vertex is V. So if you look at the picture here, it's kind of like all the immediate neighbors of A, I say I came from A to get to there. So their previous is A. And then all their immediate neighbors, like I get to F through E, so F's previous is E. I get to G and H through D, so their previous is D, and so on. And the algorithm, if you just make a few tweaks to it, will sort of do that naturally. And then when you get to the end of the algorithm and you finally dequeue the destination, which, what was it, H or I? I guess it's I. If you say, aha, I finally found I, the way you find the actual path from A to I is you follow the previous. I's previous is H. I's previous is H. And H's previous is D, and D's previous is A. And so my path is A, D, H, I. Right? So that's kind of the sketch of how you write this algorithm. A little bit harder to code, but not so bad. And it's not recursive, so some people like that aspect of it. BFS is a pretty good algorithm. Questions about BFS? Does that make sense? No question? OK. I've got a quick trigger finger. If your hand is anywhere moving around, I'll get you. Unless you're out of my peripheral vision, in which case I never call on you. Sorry. We're cool on BFS? I'm going to make you code these, you know. So if you don't know how to code them, you should ask me. OK, let me erase. OK, let's move on. Here's a little bit about the runtime. I'm not going to talk very much about Big O and runtime with graphs, but a lot of these algorithms, if you do a deep analysis of them, you discover that their runtime is proportional to the number of vertices and the number of edges. A lot of times when we talk about Big O, we talk about Big O of N. and it's usually the size of the data structure, right? But when you're analyzing graphs, a lot of times people talk about the relationship to the number of vertexes in the graph, V, and the number of edges in the graph, E. And so some algorithms are proportional to one of those things, and some are proportional to the other, and some are proportional to both. And this is basically saying it's linearly proportional to both of them. I think a naive analysis of the algorithm makes it look like maybe it would be worse than that. Maybe it looks like it would take n or v squared or something like that. I think the intuition here is you mark vertexes as visited and then you never visit them again. And so you can only mark all v of them. You know, you don't do a whole bunch of stuff for each vertex. You sort of end up potentially visiting at most all the vertexes once. And so it has something to do with the number of vertexes v. And if you have more edges, there are more neighbors, so you're doing more for looping over them to check them, which takes a little bit of time, even if all you do is loop over them. So that ends up making the algorithm be proportional to the vertices and the edges. In terms of space, like how much memory they take up, it has to do with the data structures that they use. The vector and stuff for the DFS that you're storing your partial path in, and the queue of vertexes that you're going to visit in the BFS algorithm. Okay? I wanted to show you a visualization of these two algorithms running. So let me do that right now. I don't usually do things in this way, but our 7th homework assignment is going to be called Trailblazer, and it's a graph walking program. So I want to run it for you because I mean, you're going to code this thing, but I'll show you the demo. 106B, homework 7, demo. Wait, no, solution. Wait, I guess I can't run this from the command line. OK, wait, let me run it from Qt Creator. Sorry, I knew I was going to do this, but I didn't actually prep it. So let me, solution. But I guess I can't pop that up on the screen now, can I? Because it's on video recording. Well, that's interesting. Wait, but I bet if I pop it up, it won't show the code right away. Holds his breath. SCPD students get free solution. OK, I think I'm all right. I'll compile this. So this thing, I'll launch it in a second. Basically, it pops up these different mazes and graphs and things, and you can choose these different path searching algorithms and run them, and you're going to write the code for them. And then the GUI that I provide you shows an animation of your algorithm while it's running. And so it gives you a chance to write all these algorithms and see how they work and so on. It's kind of fun. And I think just watching this thing go is a really nice visualization of the different algorithms running. So, oh, great. It didn't work at all. That's great. That's great. That's just what I wanted. I was just messing with this thing. Hang on. Give me like 30 seconds. Solution. Trail, lib, yeah, okay, solution, lib, let's try again, okay, try again. Oh, come on, man, seriously? Okay, wait, let me try one more thing. Okay, note to self, don't mess around with your project that you want to demo right before class. I'm going to run the one from the last time I taught the class. And let's all hope that that works. Okay, let me try again. Now I get to watch all the files compile again. Good use of class time. This would be a good bathroom break if you're watching on video. So anybody watch Game of Thrones last night? Yikes. No spoilers. I didn't see it yet, actually. I just heard it was cool. Okay. Please? Okay. Okay, here we go. So it's called Trailblazer, and you can pop up. These are different mazes that you can explore. So like DFS, if I click 2 spots, it's going to try to find a path between those spots. So I'm just going to click here and here. So, oops, that was too fast. Do it again. Oh, that's pretty fast, too. So it explores deep looking for a solution. And I guess that wasn't very exciting because it found a solution the first try. So, I mean, I guess any path will eventually lead out. So why don't I try from here to here? So go that way, go that way, go that way. Nope, backtrack, nope. There, I found it. So you kind of see what's happening? Like it goes as far as it can before it gives up and backtracks and tries something else. In a maze, visually, you can kind of see it doing that, right? Let me switch to BFS, breadth first search. The idea of breadth first search is we're going to go out a little in each direction until we find it, right? So let's watch this one run. Now, I think the green ones are the places it has explored, and I think it shows it in yellow if it is in queued, like it's going to explore, and gray if it already explored and it gave up and it's backtracking out of there. That's the color key here. So if I run this, it's going a little bit, a little bit, a little bit each way. Aha, I found it. And that one found a better path. It found a shorter path. And you can see it's kind of just, it's going out different directions. So like if I search from, here to here, like this top right, see, it's just fanning out sort of equally in all directions, and eventually it gets to the goal. Boom. So that's the path that it finds. If I do the same thing again on DFS, just go deep that way, that way, that way, that way. There, found it. So not as direct of a route. But, I mean, look, it depends what you want to optimize for. The BFS visited 22 locations on this particular example, and the DFS visited 15. So, it depends what your data is. Like, if it's expensive to look at them and visit them and do stuff like that, then maybe BFS is not so good in that example. Okay. I'll come back to that demo again in a few minutes.